Okay, so good morning. The midterms are almost ready. I think next week I will tell you the grades. Okay, so I tried to do it for today, but we didn't quite make it. So next week you will get your grades. All right. So what we did last time was we defined the trim point for an aircraft. Right? We made a definition for the trim point of an aircraft. So the trim point, the definition is that a trim, we call an aircraft in trim if the resultant forces and moments are equal to 0. If all resultant forces and moments are equal to 0 for an aircraft, we call it the trim point, which really means there's no acceleration, both in translation, also in rotation. Okay? So that's what we call a trim point. And obviously, because there's no acceleration, that would also correspond to an equilibrium point, right? The equilibrium point of a dynamic system. So the next thing we tried to do was, okay, if this is if those are equilibrium points, and there are many trim points of an aircraft, right? There are many flight conditions where forces and moments are equal to 0, which means no acceleration, which means constant speed, right? Constant velocity. Then that we would call a trim point. So we said, okay, let's pick one of these trim points and do our analysis. Basically, find that trim point, linearize it around that trim point, and then look at stability characteristics of that trim point. Right? So the one we chose, or I chose, was a steady level flight condition. All right? We're going to look at the steady level flight condition, which is for a passenger airplane, a flight condition that an airplane is sustaining for a long time during flight, right? If after takeoff, you go to a certain altitude, you go to a certain velocity, and for a long time, the airplane will just go steady in the air, right? That is a steady trim point. So, and if there's a disturbance, let's say there's turbulence, or there is a gust, a wind gust, we want to make sure that the airplane actually comes back to the equilibrium point, to the trim point after that disturbance. Okay, so that's what we're trying to analyze. So I said steady level flight, and we looked at the conditions for the steady level flight so that we can use the 6 degree of freedom equations and find the conditions for this flight condition. So what we did was all accelerations are equal to 0. If it's in steady level flight, there's no angular velocity, we said. We said wings level steady flight, therefore phi is equal to 0. If it's a symmetric airplane, it has to be wings level, right? So, and we said there could be a theta because there might be an angle of attack, and the angle of attack is written here. There's a W0, which means there is an angle of attack. Side velocity equals 0, which means no side slip. And we said there's a forward speed. Okay? So if we write these conditions into our 6 equations, we came up with a few conditions, which was in trim, x, y, and z, the aeropropulsive forces must be equal to these numbers. Basically, the aeropropulsive forces must be or should compensate for the weight, right? They're compensating for the weight. That's one thing we found. Another thing we found was that we looked at the 6 equations, and we looked at all the terms in the 6 equation, and we realized that the moments must be equal to 0 as well, if those equations, if we want to be in steady level flight. So all moments are equal to 0, and this is what happens to the aeropropulsive forces x, y, z in forward flight, in steady forward flight. So this is kind of our trim condition. We know everything now about the equations. We know L, M, and N. We know x, y, z, and we know what happens to all the states in steady level flight. Okay, so this is our trim condition, and this is our equilibrium point now. All right, so once I have the equilibrium point, what I can do now, I can take the 6 equations, the 6 degree of freedom equations that we obtained, and linearize these equations around this trim point. Right, that's what we did with the pendulum, and this is what we are doing over here. So if you look at the U dot equation, let me try to find the 6 equations that we did for in translation, right? We did the general equations of motion, and for the translational dynamics, we obtained these equations here. Remember these equations? 6-degree of freedom equations, u dot v dot w dot. These are the translational equations. And then we also had the rotational dynamics, which is here, right? In x direction, x body, y body, z body. So these are the rotational dynamics. So translational and rotational dynamics. So what I'm suggesting is that let's linearize these equations one by one around that equilibrium point. Let's start with the first one. Okay, let's start with the first one and try to linearize it around that equilibrium point. For instance, let's write the first equation, right? If you look at the first equation, u dot is equal to rvq blah 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 blah. So it's really, if I want to linearize this equation around the equilibrium point I found, you might want to think of this as the following: u dot is really a function, right, of r, v, q, w, x, and theta, right? Assuming that mass is constant for the airplane, of course, right? So what we are going to do now is we are going to linearize this equation, linearize around trim point, which really is the steady level flight, right? We know what the trim point is. So how do we linearize this? We have done this for the pendulum, and let's do it for this one. We use Taylor series expansion, right? So u dot would be equal to f0, right? Let's write our regular expansion here, the first few terms of the Taylor series. So it will be del r, right? The partial derivative of f at r, del r, delta r basically, and this partial derivative is a number, needs to be a number. It is calculated at the trim point. Okay, at the trim point. And the trim point is basically v is equal to 0, right? What else? Q is equal to 0. Let's go through this line. R is equal to 0, right? What else? W is equal to W0, right? That we know what that is. X is equal to some x0, and we calculated x0, it's over here, right? And theta is equal to theta 0 because theta is not really equal to 0. It must be a theta, right? So this partial derivative could be a function of the angle of attack of x0, basically the aeropropulsive force that's needed, and a function of theta 0, okay? So we are going to substitute this into this partial derivative, and you will get this one number, and this will be delta r. Okay, and del r, of course, right, would be equal to r minus r0. R0 being the steady state condition. Okay, so this is for r. Let's do it for the other ones. So it will be the same for del f, del v, right, times del r. Del v. Okay, plus del f, del q, do the same for del q, plus del f, del w, delta w. I don't have any space left here. Del f, del x, plus del f, del theta, delta theta. Okay? And then in the Taylor series expansion, of course, you have the higher order terms, but this is enough for us in order to linearize the system. And these partial derivatives, they are all calculated at the trim point. Okay? Basically the equilibrium point. Trim here, trim, and this is also trim. All right? So, very good. So let's start doing this. U dot is equal to let's try to linearize this, right? So u dot is equal to r times v minus qw plus x divided by m minus g sine theta. Okay? Good. So let's linearize using the above here. So u dot will be equal to f0. So what is f0? f0 is when you substitute the trim conditions into that function. So, right, this is a function f here. We call this one the function f, r, v, q, w, x, and theta. It's a function of these numbers. So, if you put all the trim conditions into this equation, what do we get for f0? What is r in trim? The yaw rate. Trim is 0. So this term is 0. How about this one? Q, 0. How about this term? Aha. So this is x0. So x0 is equal to, let's do that, right? x0. x0, we know what x0 is. mg sine theta 0 divided by m minus g times sine theta 0 is theta 0. What did this turn out to be? This is gone, so this is gone, so it's gone. So what you find is in the trim condition, f is equal to 0, f is equal to u dot, and we know u dot is equal to 0, so it must be equal to 0 actually. Right? Okay, so plus, let's look at the second one. We are going to take a partial derivative of f with respect to r. What is the partial derivative of f with respect to r? What is it? It's v, isn't it? Because there's no r here, so if you take the partial derivative of this function with respect to r, it will be v. So it will be v0 times delta r. Okay? So this one here is del f del r. Is that okay? So what is v0 in trim? 0, so that's gone. So that term is actually gone. There's no del r here. You see? How about the second one? How about this one? Del f del v. So far we have just zeros, right? Plus. Okay, let's do it for v. What do you get? You get r, right? r0. And it will be del v. What is r0 in trim? Huh? 0. So that's gone as well. You see? So please do the one for q plus. What is it for q? Q, you will get w0, right? Take the partial derivative of f with respect to q. What is left is w0. So you can get w0 times delta q. Yeah, because there's a minus, there will be a minus. So minus w0 times q. Okay. Plus, let's do the other one. Take the partial derivative with respect to w, you will get q0 times delta w. But q0 is 0 in trim, so that's gone, right? The final, okay, we did one, so what's left is that x, let me write it down here. Let's do it for x. Plus, what do you get if you get a partial derivative? You get 1 over m times delta x. Is that correct? Yes. And now we are going to take the partial derivative with respect to theta. What do you get? Minus g cosine theta 0, isn't it? Because it's in you're looking at the trim condition. Times delta theta. Are we done? Looks like, right? So let's write it in a clean form. Let me write it in a clean form. What did I get? I got u dot is equal to 0, 0, 0, 0 everywhere, and then I have minus w0 times del q plus 1 over m times delta x minus g cosine theta 0 times delta theta. Is that good? Good, wonderful. All right, so a few things. Are we happy with this? It's fine, right? So W0 is the angle of attack in steady level flight. I mean, it's not really the angle of attack, but it's the W component which corresponds to the angle of attack, right? M is mass, G cos theta is the geometric angle, and these are basically numbers. So it will be something like, I don't know, 1 degrees or 0.01 radians, 1 divided by mass, whatever the mass is, 1 divided by 10 tons, something like that, right? And G cosine theta, this will be a number. So basically it will be a number like 0.1, 0.02, 0.5 or something like that. So there will be numbers and there will be these deltas. Now what are these deltas? Let's take a closer look. So it is this one times Q minus Q0, right? Plus 1 over m x minus x0, right? Minus g cos theta 0, and that will be theta minus theta 0. So these are basically like perturbations, right? Perturbation from the equilibrium point, right? We have actually shown this. If you had a function like this, and the function looks like that, and you want to linearize this thing around this point, right? And let's say this is x0, everything from here, so if you put a line like that, and this is your linearization line, anything from this point will be a perturbation. For instance, this point would be, right? It would be x minus x0, right? This little perturbation would be equal to, not this point would be x, but this perturbation here, right? This one here would be x minus x0, where this one here is x, right? So any perturbation that goes from here to here, right, will be a perturbation. Okay, good. So that's a perturbation. Let's stop there for a second. One more thing. Let's look at this u dot, okay? If I would tell you that u minus u0, okay, is delta u, okay? Let's be careful here. If u minus u0 is delta u, then would it be fair to say u dot is equal to del u dot? Taking the derivative of both sides, this is u0 in trim, therefore it's a constant, so this will go, so u dot is equal to delta u dot. Would that be fair? Yes. Okay, so which means this is actually equal also to del u dot, this equation. So I could actually write this equation like this. Del u dot is equal to minus w0 times delta q plus 1 over m del x minus g cos theta 0 times theta delta theta. Would that be fine? Okay. If you look at this, every variable in this equation is a perturbation from the trim point, isn't it? It's a perturbation from the trim point if you look at this equation. Okay? Therefore, this is, okay, we linearize it. It's a linearization of our previous equation. But at the same time, it is a perturbation equation, isn't it? It's a perturbation equation. Everything is a perturbation. So I have the dynamics. Let's put it this way. Now I have the dynamics, the differential equation that represents the dynamics of the perturbation variables. So in other words, if the perturbation variables all go to 0, they are all perturbations from the trim point, right? So if all perturbations go to 0 as time goes to infinity, which means everything goes back to the trim point, isn't it? So that's what I'm after here, what I'm trying to do. I will try to make sure the perturbation equation actually is stable, which means the perturbation equation goes back to 0, which also means that the perturbations will become 0 as t goes to infinity, and therefore the aircraft goes back to its trim point because perturbations are equal to 0. So what I'm going to check from here on is that are the perturbations actually going back to 0 or not? If the perturbations go back to 0, it means no perturbation. No perturbation means go back to equilibrium point. Okay? So this one here is sometimes called a perturbation equation. Perturbation equation. Okay? And the perturbations, note that the perturbations are not very big. These are small perturbations. Why are they small? Because they are coming from the fact that we linearize this. Okay? And linearization is only true for a small neighborhood. This is not true for the whole neighborhood, you know. If you have a function like that, a nonlinear function, and you linearize it around that point like this, this line is not an approximation here or here. The line is quite different. But in the small neighborhood, it is similar. So therefore, these perturbations from that point are only valid for small perturbations when they're small. Okay? So therefore, these perturbations are small perturbations. And if you look at this equation, it really is a perturbation equation, but with small perturbations. Okay? So, what does this equation tell me? It tells me if there's a small perturbation, then if the perturbations go back to 0, then no perturbation, therefore it goes back to trim. So what I'm going to check is I'm going to check the stability of this perturbation equation. Okay? This is not any different from what we have done before. It is still, we're still going to look at the matrix, still look at eigenvalues. But this is a different angle to explain this. We linearize it, but we ended up with a perturbation equation. Therefore, in a lot of books, this linearization looking for stability business, it's under a topic called small perturbation theory. Okay? It's called a small perturbation theory, or sometimes a small disturbance theory. What this theory does is exactly that, nothing more. You linearize it. Linearization is a perturbation around an equilibrium point. The equations that you end up at the end are perturbation equations. And the idea is if the perturbation variables, which means delta u dot, delta q, delta x, if everything goes back to perturbation, if the perturbations here, the big perturbations are equal to 0, then we are in trim. Okay? So this is kind of the idea here. And we will talk about small perturbation theory in a second. But before that, let me show you a few more things. Okay? There are many ways to rewrite this equation. For instance, let me start here. For instance, what is Q0 in trim? I mean, what is Q0? It's Q in trim, right? The angular rate in trim. So what is it in trim? What is Q0? 0. So this is equal to 0, right? So basically, you know, delta Q, okay, is equal to Q minus Q0. But because this is equal to 0 in trim, not always, in this flight condition, I mean, in steady state it's 0, therefore delta Q is actually equal to Q. Right? Just because we chose the steady state as, just because we chose the trim condition to be Q equals 0 in steady state, right? So that's that. What is x0 here? Well, x0 is not equal to 0. x0 is equal to mg sine theta 0, right? For here. How about this one, theta 0? So that is not equal to 0. But you could safely say, for instance, this equation you could rewrite like that. You could rewrite it like this. U dot, or let me remove this. You could write it like this. U dot, and U dot is equal to delta U dot. So you can interchange all these things. You can make W0 times Q plus 1 divided by M times delta X minus G cos theta 0 times delta theta. Okay? So what do you have? You have perturbation equations here. You don't have a perturbation here, it's just Q, and you don't seem to have a perturbation here. So is this still a perturbation equation? The answer is yes, because it is the same equation. The reason I'm writing Q instead of delta Q is because Q0 is 0. Okay? So in a lot of books, right, you might see something like that and you might say, what is this equation? There are perturbations here, no perturbations there, so it's kind of a Frankenstein of equation. But in reality, it is still a perturbation equation. The reason we are not writing the Q0 is because it's 0. But it's still a perturbation equation. How about this one? When I first started out writing this equation, forget about this delta U dot. Look at this one. Was this a perturbation equation? It still was. I just told you I'm going to linearize it. But since U dot is equal to delta U dot, it is a perturbation equation. It is still small perturbations. Okay? So you could do this. You could do this. First of all, you have any questions here? You understand that when I linearize it, it is a perturbation equation with small perturbations. Okay? All right. So you could linearize this for other equations as well. And let me write you, for example, V dot. And you can really try this at home. Okay, I don't mean to spend a lot of time here. This will be del U0 times R plus W0 times P plus 1 over M times delta Y plus G cos theta 0 times phi. So this is the perturbation equation or the linearization for the V dot equation. Linearized around trim point. Okay? So you should get this. So now look at this equation now. I have a perturbation here, del y. These don't seem to be perturbations. But are they perturbations? What did we learn? Yes, they are perturbations. If I linearize it, they must be perturbations, right? In fact, it means that this is probably something like that. Del V dot is equal to minus U0 times delta R times W0 times, plus delta P plus 1 over M plus delta Y plus G cos theta 0 plus delta theta. So these are still perturbations. Okay? So why am I writing R instead of delta R? Because delta R is equal to R minus R0, and in trim R0 is 0, therefore R is equal to delta R, therefore I can write R. Okay? Let's look at the second one, P. Del P is equal to P minus P0. P0 is 0 in trim, therefore del P is equal to P, so that's that. Delta Y, you can't really do that. You could do it because Y0 is equal to 0, but I still left it as delta Y. And, I'm sorry, this is phi here. This is phi. Okay, so delta phi is equal to phi minus phi 0. And we know phi 0 is 0 in trim, and therefore this is that. How do I know what is in trim and what is not? We did this last week. Please look at the videos of last week if you missed that class. Okay, so it is still a perturbation equation. Now this is a perturbation equation for the second line. Can you do it for the third one, for W, for the W dot axis? Yes. Can you do it for P dot Q dot R dot? Yes. So do it for every other equation, and we have 6 linearized equations which are all perturbations by themselves. Okay? So let me write down W dot. The W dot equation would look like this. Del Z divided by M minus G sine theta 0 times delta theta plus u0 times q. So that would be the third equation if you linearize it at home. Okay, so let's call this one equation 1. This is the linearized equation here. This is equation number 1. This is equation number 2. And this one would be equation number 3. Basically the linearization of the translational dynamics around the trim point for an aircraft in steady flight. Does it make sense? Okay. Any questions so far? All right, so I'm going to do this from another angle now. I'm going to obtain the same equation using actually small perturbations, and we'll look at it from that angle as well. So let's look at this from a small perturbation or small disturbance point of view. Do the same thing with small disturbance theory. So what we do in small perturbation theory, it is the same thing. It's just looking at a little bit different from a different angle, but it's really the same thing. We will obtain the same equation. So what we're doing here is the following. Let's perturb each state in the equations of motion, around their trim points by small disturbances. All small perturbations. Okay? So what I'm saying is, take that equation, our equation, that u dot equation. U dot is equal to rv minus qw plus x divided by m minus g sine theta 0. Okay? This is our 6th equation. Take that equation and perturb every single variable around the trim point by a little bit and see what the equation will look like. What I mean is this. Take, for instance, u dot. Okay? Take, for instance, u dot and perturb it. Instead of u dot, just write delta u, meaning that u dot minus u0 dot, which is equal to 0. So this is kind of easy. But r, meaning that perturb r by r minus r0. Perturb v by v minus v0. Okay? Perturb q by q minus q0. And so on and so forth. So let's try to write that into these equations. That's what this theory will tell you. So, for instance, for u dot, I'm going to write del u dot because it is already u dot, so we know that. U dot is equal to, so for r, I'm going to write r minus r0 times v minus v0. No, I'm not going to do that. I'm sorry. I apologize. This is, of course, not true. What we are going to do is the following. Since del r is r minus r0, I can safely say r is equal to del r plus r0. Now that's the correct one. Can I say that from here? If delta r is equal to r minus r0, r is equal to del r plus r0. Right? So you can do the same thing with this one. You will get v is equal to delta V plus V0. And for Q, for instance, you will get Q is equal to del Q plus Q0. Would that make sense? Because, for example, if I had something like this, and this would be a nonlinear system, I think I just wrote this, and if this one here is x0, right, the new x here would simply be x0 plus delta x, right? So if this is delta x here, if this is delta x, if this is delta x, then x0 would be x0 plus delta x, so that would be this number. So this would be equal to x, the new point. So this is exactly what happens here. R is equal to del R plus R0. You understand that? This is getting too confusing now. Let's start from here again. This is our equation, right? So what I'm saying is every perturbation can be written in R minus R0 and so on and so forth. So then you can obtain each of these variables from these perturbations. So R is equal to the perturbation plus this, plus the trim point and so on and so forth. So you get every variable. So what I'm saying is write each of these variables into these equations, into this equation. So which really means it is still the same variable. Okay? So what you would get here is, since this is true, we can write this now. U dot is equal to, instead of R, I will write del R plus R0, V0 plus delta V. Okay, that would be, I'm writing this instead of V, this one here. Minus, instead of Q, I will write Q0 plus delta Q, W0 plus delta W, plus X0 plus delta X divided by M, minus G sine theta 0 plus delta theta. Is this okay? And this is still equal to, since U dot is equal to del U dot, so it's still equal to this. It is still the same equation, isn't it? This and this is still the same equation. Just replaced the variables with the perturbation from the trim point, which is still a variable. So it is still the same equation. Does that make sense? Very good. So if that makes sense, then we are out of the woods. It's going to be easy from now on, if you understood it so far. So, what is R0 in trim? Now I'm going to write this in trim now, right? What is this in trim? R0 is 0. So, okay, this is 0 in trim. How about V0? 0 in trim, right? Q0, 0 in trim. W0, not 0 right now. X0 and theta 0, so these are not equal to 0. Good. So we made at least some progress. Continue. It will be del R times delta V. Now look what my perturbation equation is becoming. Del R times delta V. Here I will get minus del Q times delta W and minus W0 times delta Q. Right? This one here. Just multiply this one by one. Okay? All right. And here I get plus X0 was equal to mg sine theta 0 plus delta x divided by m minus g times sine theta 0, plus delta theta. Any questions? What I'm doing here? Any questions so far? I know we seem to be writing a lot of equations, but I keep writing the same equation really. I mean, there's nothing very exciting, right? I just rewrote everything. It's still, this equation is still equal to that. So it's still the same equation. So, any questions so far? Just multiply this with that, so I just open this up. Is that fine? Okay, so here is what we do. Okay, I have to deal with this sine though. I haven't dealt with the sine. Before it gets too confusing, let me just do the sine here. Sine theta plus delta theta, I can rewrite this as sine theta 0 plus cosine theta 0 times delta theta, right? If you have two angles, you can add them in sine, you can write it like this in terms of sines, and right? Okay, so this will be this. How do I get this? I get it like this. If you have an angle sine theta, okay, you can have a Taylor series expansion for this one. It will be sine theta 0 plus cosine theta 0 theta minus theta 0. This is Taylor series for sine. It's for sine theta. Okay? So it will look like this. So instead of sine, you can also write sine theta 0 plus delta theta, and then it will be equal to this basically. Sine theta 0 plus cosine theta 0 times theta 0. It's basically a linearization of sine. So that's how I got this. Okay? So this is what I'm going to write over here in terms of sine in order to make the small perturbation for this angle. So at the end we will have u dot is equal to del r times delta v minus delta q times del w minus w0 times delta q plus mg sine theta 0 plus delta x divided by m minus g parenthesis sine theta 0 plus delta theta. Okay, so this is my perturbation equation. Basically, I rewrote everything in terms of perturbations. Okay, now what we need to do here is, first thing, since these are small perturbations, a perturbation times a perturbation will give you what? Hopefully a very small number, because if this is a small perturbation, you multiply it with a small perturbation, it will be even a smaller perturbation, right? So what I'm saying is this is really close to 0 because it's a really small number compared to everything else. It's one order of magnitude smaller than everything else, right? Small perturbation times small perturbation. Same thing here, small perturbation times small perturbation, really small number. Because delta q is supposed to be small. It's supposed to be a small perturbation. Here I have to keep this one I have to keep, and this one I have to keep. Oh, here I made a mistake, of course. This is, no, okay. So, what do I have? I have minus W0 delta Q plus G sine theta 0 plus del X divided by M. And let me write this one here, replace it with my sine here that I have, minus G sine theta 0 plus cosine theta 0 times delta theta. So these are gone. And I have del u dot is equal to minus w0 delta q plus del x divided by m minus g cosine theta 0 times delta theta. Compare this with the equation I just found 10 minutes ago by linearizing the equations. Or this one here. Is it the same equation? It's the same equation, isn't it? So it looks like we did the same thing. On one hand, we linearized the system around the equilibrium point. And the second one, we just replaced everything with perturbations. And we obtained the same perturbation equation. So linearizing the equation and using small perturbation theory, basically giving perturbations, will give you the same result. Linearization of an equation around an equilibrium point also means writing down a perturbation equation. Okay? So small perturbation theory is nothing but linearization. But knowing that every variable in that equation is really a perturbation or a disturbance from its equilibrium point. And if the perturbations go back to 0, that means there's no perturbation around the equilibrium point, therefore everything is back to its trim point. So the idea is to check the stability of the perturbations to see if they are going back to 0. If they go back to 0, then we are in trim. That makes sense? Okay, so let's give a break and we'll continue.